once again, thanks to the DPDK community for allowing myself and Keesang to share this our experience working on this area. So let me keep it brief and short. Our agenda is very short. That is what had driven us to go and look at the ML library and why it became a priority for us and how we try to combine a couple of hardware and software ecosystem solutions together under AMD to address under ML Dev. What were the challenges? What were the opportunities? And what we found we can improve. These are the three major things that I would like to talk today. Okay, so to the problem statement, as usual, we have a virtual RAN vendor who actually was using a 64 core AMD EPIC SoC, and they were trying to run the VRAN in containers. So they have the base CPU, they have the accelerator, NIC cards and all. And on top of that, they were running on the bare metal, they were running the containers where just like yesterday, where we highlighted different functionalities were running for this in cell 1, cell 2, cell 3. Each of these functionalities were driven and written such a way that it is running inside one container and one pod. So doing this methodology, what they were able to achieve was running up to 3 containers uh, by making use of almost around 58 CPU threads and all. And what they with zero acceleration, okay, no FEC offloading, nothing, everything done on the CPU. And what they were trying to see is that if I if the end customer go and use some ML accelerator, can they run up to 5 instances? That was a target that they were trying to set and try to explore. So when it came to us, we shared the Xilinx team and we shared it to the AECG team, which is internal to the EPIC SoC team, wherein which we all three came together and tried to explore what all could be offloaded in terms of ML. So 2, 3 options came up. One was on the radio side, one was on the DU side, and one was on the RIC side. So what interested the customer was on the what could the channel prediction and channel equalization. If we can save some CPU threads, CPU cycles there, it would be excellent for them. The MAC2 scheduling, if based on our tile architecture, if some kind of scheduling and optimizations could be done, that could also save some CPU threads for them too. So these were the two major areas that the end customer was trying to look in to reduce the number of threads. So with the reduced number of threads, they can achieve at least one or more container, which can at least do, instead of doing a 28 cell scenario, at least they can do a 9 cell scenario with the extra threads that were saved. This was their target. So run 2 or 3 instances of 28 cells on 32 core, and that is SMT, and remaining threads try to run at least 9 cell each. So thereby getting up to 5 instances or 6 instances of it altogether. So for the end customer, for them it was very straightforward. They have their application along with the VRAN application. The VRAN application somehow magically would talk through ONX runtime by loading custom models to run on CPU or run on the V70 card accelerator. This is what they were looking at. So the models were custom built. The model ran on the V70 card as well as on the CPU too. Now, for us, what it meant to us, like since we had been collaborating and working with the customer for the last 1 year, we knew that their applications is completely written with using DPDK libraries. And from what they were trying to say is that depending upon where it is, like if it is in a densely populated area where power is less of a constraint, they would have an accelerator. If it is at the suburban area, they might be running it on the CPU, or it could be a mix and match of things like for IoTs and other things, they might be using CPU related activity where the data is not dense. And for heavy data traffic and heavy cell scenarios and all, they would be using accelerator. This is what we were able to understand and analyze from their request and all. So same network card, same accelerators. Only thing is that depending upon the number of cells and its density, it might keep on varying whether they run it on the CPU or on the accelerator. Now, here's the tricky part. AMD to start with did not have any ML based DPDK PMD into place. But what we had was the SendDNN library, which optimizes the ONX and PyTorch and all. We have the XRT library that was available to talk to the GPU and the FPGA as well as the V70 card and all. So what we did was, like, after closely working with them, we identified, just like what we highlighted, we could intercept certain work patterns on the high field layer for the channel estimation and quantizations and all. We could do something in the MAC layer and all. So we created a simple callback into there with the early patch that was released by the Marvel team. We took it and we created a small call into those function codes at that layer. And what we did was we created a simple virtual device, VDEV device, wherein which, depending upon where it is running, if it is running on the CPU, and if we give the VDEV thread instance, number of thread instance as 0, then it would go and call the XRT library, which will probe and identify whether there's a GPU or a V70 card. If we give the thread instances as like 2, 4, 6, 8, etc., it would treat it like it would be calling the CPU. So instead of going through the XRT library, it would call the ONX to run the Zen DNN on the CPU part. So this was a simple trick that we did. So whether it is a physical device, PCI card, FPGA or not, we just use a virtual device VDEV by passing the parameter given to it. If number of threads is set as 0, it first explores with the XRT library to identify the V70 card. If number of threads is set as 8, 16 or 32, it would then understand that it has to run on the CPU and call the send in and optimize the ONX to it. So as I highlighted, we created a simple VDEV device here. And if you don't pass anything, it will go and query for the XRT library to identify the device. If it is passed with the parameter like num threads, it will then give the priority of trying to run it on the CPU. This is what we, as a proof of concept, we started with. So, but we had certain hiccups there to make this work and get it adapted to run on both instances, that is a device as well as on running on CPU. What we did was, whenever we do a NQ or DQ, we supplemented it with an additional ring buffers here. So all the NQ DQ is held in software by the ring buffer, all the input output ops payload, all the descriptors and all, it is held in a ring buffer here. We had one control thread for each ML device, which was a which actually dequeues the descriptor that was enqueued by the user and send it to the appropriate device. So if it was the V70 card, through the XRT library, it would send the request. And if it was through our ONX runtime environment, we used to send the buffer to be processed to the ONX environment and all. So this is one work that we did extra into the standard template what Marvel team had shared. We added this extra layering so that it becomes device CPU or hardware device agnostic in nature. Then we did had a look into IO quantization and all. Yes, it is optimized today for Neon. We are from the ZenDNN library part. We have APIs which actually works and quantizes the data using SIMD and all. So now we are trying to figure out whether we expose that functionalities out and write a simple wrapper on top of it, or allow the user to directly just pass the data, and underlying the ONX library part, everything just takes care by the ONX. We are like debating in that part too. Okay. So what are our opportunities here that we found? We can create a single VDEV device by passing an extra parameter. It gives a priority whether it should probe through the XRT for the PCI device, or it should be looking at running at the CPU point of view. Or we can pass both as two VDEV devices. We can pass one to pick up the PCI device through XRT and other one to run it on purely on CPU. Like that we can do. Then we ended up using MBUF extended, where we were asking our XRT to expose DMAable memory regions to do and reduce the memcopy part too, so that the user buffers can be used. But this is still, there is a couple of problems here. It is only a single queue that is supported. We are working to enhance this and all. Now, the ring and buffer model that I showed earlier, this was actually borrowed. This idea was borrowed from the software skeleton DMA, where we had a single dedicated control thread that is generated from the PMD, which actually does the work for you. Same model we executed here. So it is mostly like cut and paste from it. But these were the things that we added extra to make our logic work on complete one AMD ecosystem. Now, like I pointed out, telemetry is missing. If we can add some telemetry with regard to whichever, whether it is CPU or whether it is tile or whether it is our V70 card, it would be very useful. That was one of the comments that we got. Now, the second thing that we are like I talked about was on the quantization. Already, we have sent DNN library, which actually, when any calls to the ONX takes place, the libraries are optimized to do the conversion and all. How to bring that or expose that is what we are trying to figure out too. And certain limitations what we have today, I have not exposed the extended stats from the device or V70 card yet. It only works with pre-compiled models and all. But at least with this minimal changes and with the working model from the RFC patch, which got integrated in 23.11, we were able to showcase this proof of concept to the customer. So the next activity is going and showcasing this demo in MWC and getting it worked out, while we are working on trying to get this pushed in 24.11, which is tough, but at least by 25.03, be able to get this exposed out, at least as a RFC out. This is our plan with regard to the ML and our activity done so far on the ML dev. That's what I had to share in the small talk. Thank you.
Vipin, I just have one question. I would like
Hi,
to understand.
Srikanth.
Hi. Good job, actually. I'd like to understand what are the limitations that you see in the current spec. I mean, more I would like to understand from what are the areas where we can improve.
Thank you. I think I got the question. Let me try to answer it. Srikanth, it's not a limitation on the ML dev library, but like I pointed out, AMD has 3 to 4 different ways of running ML. One is purely on the CPUs, which supports the VNNI and other instruction sets. We have a dedicated V70, like it's a DSP with certain MIPS kind of cores and all. We have a FPGA variant of it, and we have GPU variant of it. The struggle that we were facing is based on the customer deployment, like if it is in the suburban area or if it is in the remote area and all, the power and other factors affected where the user did not have the right power to plug in an multiple or single accelerator card to do it. So they wanted a single simple interface which allowed them to do it. So we ended up exposing all the devices, that is both CPU, V70 and our GPU, not every GPU, selected GPU through as a VDEV. And when we do the probe functionality, we just go and check based on the argument given, whether we have the particular device plugged into that platform. If yes, run it on that, or if not, fall back onto CPU. It's not a limitation in ML dev library. It is what we had to do something to accommodate what the end user wanted.
Yeah, I mean, my question was more focused on what are the areas that, I mean, since you are one of the user who has actually used the spec, right? We just want to understand what are the areas in which we can make more improvements so that it would be
telemetry. Of course, yes. Telemetry is one big important thing, which is key thing to expose all the values out so that the orchestrator or the central node controller can do many things too. So that is something that I would recommend to see. I'm happy to work on that with the team and DPDK family on that area. That would be the immediate thing if you ask me.
Sure. Thanks.
Thank you.